Section 4.2, we're going to talk about binomial distribution. Many probability experiments can be thought of in terms of just simply two outcomes, success and failure. For example, flipping a coin, getting heads can be called a success, not getting heads can just be labeled as a failure. When you're rolling a die, getting a 2 could be considered a success, and getting anything else could be a failure. Any probability where you can reduce it to just two outcomes is known as a binomial experiment. Now, a binomial experiment has to satisfy the following conditions. The experiment has to have a fixed number of trials where each trial is independent of the other trials, meaning that the probability of one event occurring does not affect the possibility of others. There are only two possible outcomes, which can be classified as a success or failure. Probability of success must be the same for each trial, and the random variable x will count the number of successful trials. So if I want to determine the probability of exactly x successes in n trials, we have the following probability formula. So the probability of x successes will be equal to, and you're going to notice here many variables. N is the number of trials, and x is the number of successes that we want to find the probability of. And you can see, first of all, we have n and x on the combination notation that you've met previously. This is the same symbol. The letter little p is the probability of success in a single trial, and q is the probability of failure in a single trial. So using this formula, we can calculate a lot of probabilities quickly and simply. In this first example, we have rotator cuff surgery has a 90% chance of success, and the surgery is going to be performed on 3 patients. In number 1, we want to find the probability of the surgery being successful on exactly 2 patients. So the first thing that we're going to want to make sure that we're clear about is what we're deeming a success and what we're dealing a failure. So the successful surgery, I'm going to assign to the letter S as a success, and an unsuccessful surgery, meaning they were not able to fix the problem with the surgery, I'm going to assign as letter F. Whenever you have a binomial probability where there's only two outcomes, one labeled the success and one labeled the failure, the next thing you're going to want to do is lay out the values you're going to use for the variables n, p, q, and x. N is supposed to be the total number of trials. So back up here, we were told we're doing the surgery on 3 patients. That's our number of trials or surgeries being performed. So n should equal 3. We want the probability of being successful on exactly 2 patients. X is the number of successes we're looking for, so that would be 2. Little p is the probability of being successful. And we were told up here that the probability of being successful with this surgery is 90%. And remember, 90% written as a decimal would be 0.90. When you record little p, it does need to be a decimal. Little q then is supposed to be the probability of failure. Now, most people would quickly understand, okay, if there's a 90% chance of success, then there's a 10% chance of failure, which is correct. You can always get your q value by doing 1 minus little p. As you can see in this case, 1 minus 0.90 would give me the same answer. Once you have your variables set up, then you're just going to substitute them into the formula. So the probability of 2 successes is equal to, the formula says NCX times P to the X, Q to the N minus X. Next, we substitute the values for the variables. So we're going to compute 3c2 times 0.90 to the second power times 0.10 to the n minus 2 power to the 3 take away 2 power. So in total, we want to calculate 3c2 times 0.90 squared times 0.10 to the first power. When you type this into a calculator, I would always be really careful here and put parentheses around your C, which again, the usual way that gets typed in is you put the 3 first, you hit your NCR key, then you put in the 2, and then you can use your times symbol 0.90, use your exponent key to put the squared on there, and then times 0.10. When you calculate that, you will get 0.243, or roughly a 24% chance that this would occur. Now, if you look in your book and you look at example 2, they go through how you can also arrive at the same answer using a tree diagram. Feel free to take a look, but you'll find that the formula is usually much more efficient in terms of performing these calculations. Number 2 modifies the first example and says, find the probability of the surgery being successful on at least 2 patients. You need to understand what the words at least 2 mean, which sounds like a simple thing, but when you're calculating probabilities, it's really important. If we want to have at least 2 successes in 3 total surgeries, what we're really looking to know is the probability of 2 patients having successful surgery. At least 2 does include 2. It would also include the probability of 3 patients being successful. So in this case, we need to take P of 2, which I already know because I calculated that above, and I need to add P of 3. Well, P of 3 can be found by writing out this formula and changing the X value, which was previously 2, to 3. So that would look like 3C3 probability of success with the number of successes you want as the exponent times the probability of failure, and the exponent here is supposed to be 3 take away 3. As we said before, P2 is 0.243. When I perform the next calculation, there's a couple of things you can do here to make your life easier. The first one being, at the end here, 3 take away 3 is 0. Anytime you have something raised to the 0 power, it equals 1. So therefore, 1 times stuff just gives you that stuff. So in other words, we can drop off this final factor that is equal to 1. So now we just have 3C3 0.90 to the third power. And one last simplification, you get to know some shortcuts after you've worked with these notations for a while. Anytime the 2 numbers on your C are equal, that is always equal to 1. Because you're saying, I want to take 3 objects and use all 3 of them in a group. Well, if you have 3 objects and you want to use all 3 of them, there's only one way to do that, and that's take all 3. So this calculation, which was complicated, by knowing a few little bits of information, I can simplify it to really just this. Now, if you don't like remembering those extra bits of information, you can just go back and type this line entirely in your calculator and it'll do the math for you. But doing this thinking kind of minimizes what you actually need to type in. When you add these two together, you get a final answer of 0.972, or about 97% chance that at least two of the surgeries will be successful. So, again, understanding how to interpret at least two or at least any number out of a total is very important to be able to do. Let's take a look at another example. Again, this one's been modified because I updated the data. So I went to a 2019 survey and looked at only US adults aged 18 to 24, and they were asked which social media platforms they use. The results are shown in the figure. 6 people who participated in the survey are randomly selected and asked whether they use the social media platform Facebook. Construct a binomial probability distribution for the number of 18 to 24-year-olds who responded yes. Now, we learned about probability distributions in the previous section. Remember, probability distributions are just made up of each possible outcome and the probability that it occurs. First, I'm going to identify what would be a success and what would be a failure. If we're choosing 6 people and asking whether they use the social media platform Facebook, obviously each person is either going to say yes or no. I'm going to assign yes to be the success, and I'm going to call no the failure. Technically, though, you can reverse these. Just because we use the terminology success and failure doesn't mean that we can't use them the other way. You could call a success not using Facebook. In fact, some people might think about things that way. And you could call a failure using Facebook. The math's going to work out just fine whichever way you set up your success and failure. Next, we need to know the possible outcomes. So if we are going to ask 6 people, what are the possible outcomes that might happen? We might have no people report they use Facebook. 1 person might say yes. 2 might say yes. 3, and so forth. So there are 7 possible outcomes for my survey. So what we learned in the last video is that in a probability distribution, you would list your possible outcomes, and then next to each one, we need to calculate its probability. So my possible outcomes, again, are 0, 1, 2, 3, 4, 5, and 6. And since I can think of this as a binomial probability, I can calculate those using our formula. The probability of X successes is always NCX times P to the X power times Q to the N minus X. So for example, if I want to calculate the probability that none of the people use Facebook, I'm going to say the probability of no Facebook users would be equal to, and now I need to know the values for all my variables. So I'm going to go to the side for a moment and say, okay, how many trials am I completing? Well, how many people am I asking? 6. What is the probability of a success? Now, the way I've defined success is they are a Facebook user. 76% of the people in this survey reported that. So 0.76 should be my probability of success. Q is my probability of failure. If 76% report they do use Facebook, what percent report that they don't? I can always find that by doing 1 minus my probability of success. And in this instance, I get 0.24 as my probability of failure. And X for this first example is going to be 0. I want no one to report that they use Facebook. Now I'll substitute all the variables into the proper locations. And once I've done that, again, there's some simplification that can happen here. 0.76 to the 0 power, anything to the 0 power is going to equal 1. And 1 times these other two terms will just be the result of multiplying those other two terms. So now I've gotten it down to the point of just needing to calculate 6C0 and then times 0.24 to the 6th power. When you type that into a calculator, you get this probability, which is a pretty small number. Technically, our original data was given to 2 decimal places, so I should round this to 3 decimal places. And to 3 decimal places, it's actually just 0.000. So it looks like there's absolutely no chance that's going to happen, but in fact, it's just very, very, very small. Now, what's neat about this formula then is when it comes time to calculate the next value, I can just go back and change one thing. If I want P of 1, everywhere I had a 0 before, I'll just knock that out, replace them all with 1s. I need to calculate 6C1 times 0.76 to the first power is just the same as 0.76 times 0.24 to the 5th. And just by doing some quick editing of what I just typed in my calculator, I can now calculate this value. So this time I get approximately the decimal 0.0036 rounded to 3 decimal places. That's going to be 0.004. And again, everywhere I had a 1, I can just go back, erase that. I'm now going to put in 2's everywhere. And I can go to my calculator and calculate this value. You should try typing in the rest of these yourself and make sure you're able to use your calculator correctly. And in a moment, I'll show you what values I got, and that way you can compare them. Here are the correct values for all of the probabilities. So this is the probability distribution that I was asked to calculate. And of course, we could now turn that into a histogram if we were interested in doing so. And if I sum up all of these probabilities, they do actually turn out to equal 1. In reality, sometimes that might not occur because when you round these numbers, you introduce a little bit of error. So it's possible you won't get exactly 1, and that's okay as long as it's really, really close to that.